please hit subscribe.
In the previous video, we showed the ratio test for sequences, and we showed some examples on how it is used and the intuition behind it. In this video, we will give a proof to the test. Let us first state again the statement of the test. So the test says that if the limit of the ratio of two successive terms in the sequence as n approaches infinity is not equal to 1, then the sequence a sub n either diverges or converges to 0. So this is the test that we have used in the previous video. Here we will just prove this. So to do that, we will notice that this hypothesis where it says that it's not equal to 1, that this limit is not equal to 1, can be broken down into two cases. The case when the limit is less than 1 and the case when the limit is greater than 1. So both cases cover this case when it's not equal to 1. Now the test says that if it's less than 1, then the sequence converges to 0. That means the limit of the sequence is 0. And that if the limit here is greater than 1, then the limit of the sequence is infinity or negative infinity. It diverges. And then let's just recall that because the hypothesis does not say anything about the case when the limit equals 1, then if the limit equals 1, we really do not have any idea as to the convergence or divergence of the sequence. We will have to look at the given from a different perspective or apply a different kind of test. So this test is powerless when the limit of the ratio is equal to 1. Now let's prove these two cases when it's less than 1 and when it's greater than 1. We begin by showing the first steps that are common to both proofs. So the first step is to just call the limit, which we assume exists. So the limit here is either less than 1 or greater than 1, and for the case of greater than 1, it could be infinity. So let's assume that limit exists. Let's call that limit L. Now we will apply the precise definition of the limit. So to review the precise definition of the limit, you can click this link here and it will take you to our video on the precise definition of the limit. Now the precise definition says that this statement here means that for all positive number epsilon, which we can choose freely, whatever number that is, there exists a natural number m sub epsilon. The subscript means that this number may depend on our epsilon. This number exists such that for any natural number k that is greater than that m sub epsilon, this statement holds. So this bit here is what we have here inside the limit, and L is our limit. This distance between the limit and our ratio can always be made less than epsilon. So that's the precise definition of the limit. Now let's do a little bit of manipulation here. So first let's remove the absolute value symbol. And when we do that, we get this equivalent expression. So we recall that absolute value means plus or minus that expression. And so when we have this inequality, we get this inequality. Now let's add L to all three sides of the inequality and we obtain this expression. Now we are ready to prove each case in the inequality, in the test rather. So to prove the convergence case, we will put we will put the expression here into a form that looks like this, where we have the desired limit here and it is sandwiched by two zeros. And if we can find a statement that looks like this, where we have an expression here that goes to 0 and an expression here that goes to 0, then we will be forced to conclude that our limit is in fact 0. So the first step is to take this right side of this inequality. This is what we get. And here we are using n instead of k because here n approaches infinity. That means we can always make it as big as we want. And the only condition that this be true is that n be greater than m sub epsilon. That's the only condition. And so here we are implicitly assuming that n is greater than m sub epsilon. This wouldn't work if we are using n less than m sub epsilon. And here we have e epsilon plus l, and l we already know. Our guess is that L is 0, and so let's just replace that with 0 and we are left with epsilon. Then the next bit is we just add the obvious restriction that this limit, or rather this expression here, this ratio, must be greater than or equal to 0 because it's an absolute value. And then we multiply all sides by the denominator, and this is what we obtain. Now, what we notice is that what this is saying is a given term must be less than the product of epsilon and the preceding term. So this is, if we are looking at this term, then this is the preceding term. And we can see that this holds for any value of k as long as it's greater than m sub epsilon. And so we can actually use this for n minus 1 as well. So we can just replace the n here with n minus 1 and replace the n minus 1 here with n minus 2 as long as these two things are greater than m sub epsilon. And then if we multiply both sides by epsilon, we get this expression. We get epsilon times this and then epsilon squared times this. And why did we multiply with epsilon? Because we wanted to get an expression with a term that is the same as this term here. Now we have this term, and we have this term, they are the same, and so we can make a chain of inequality. So 0 is copied here, a sub n is copied here, it's less than this expression, this expression, this expression, which is less than e squared, epsilon squared times this expression. Now we can do that again. We can do the same process again, and before we do that again, let's just show this clearly that we can actually just eliminate this middle expression here and we will be left with this simpler expression. And we will repeat this step here for n minus 2 here. So this is what we get, n minus 2. And then here, instead of multiplying with just epsilon, we multiply with epsilon squared so that we match the expression here. And again, we can chain it in this manner, and this becomes the simpler statement. So you notice we can do this again and again until we reach k, which is greater than m sub epsilon. And the final reduction would look like this. We have epsilon raised to the n minus k times the absolute value of a sub k. So that's the minimum term that we can do it for, because we cannot go less than k. And then this is a very good form because first we remark that epsilon can be any number. We can choose it to be any number. But if we choose it as something greater than 1, what we get is the limit of this term here goes to infinity. So 0 is less than, the limit we're looking for is less than infinity, which is always true. So it doesn't really give us information. It's true, but it does not give us information as the value of a sub n. what we can do instead is choose epsilon to be less than 1, because by doing that, if we choose an epsilon that is less than 1, we can make the following claim. This limit here, if epsilon is less than 1, if we apply the limit operation, limiting operation, you see that that is 0. A number less than 1 multiplied by itself many times gets closer and closer to 0. And now we are in the form that we intended to be. We have 0 and 0, and sandwiched is the limit we're looking for, and therefore this limit is equal to 0. And because we have shown that this limit is equal to 0, what that means is that our guess that L equals 0 is correct. L equals 0 means the series or the sequence converges. Now we will look at the divergent case, where the limit of the ratio is greater than 1. And to show this, we are going to find a statement that says that the ratio here is greater than some expression, and this expression here goes to infinity, and therefore the limit of the ratio is also infinity, because only infinity can be greater than infinity. So we start with the left side of this inequality, and like what we did in the previous proof for the convergent case, we multiply both sides by the denominator. We obtain this, and again, we see what this expression means, what this statement means. It means that the given term, is greater than that term before it, or the previous term, times this term here. And that's true for any n greater than m sub epsilon. That's the only restriction here. And then, because it's true for any natural number greater than m sub epsilon, if we have n minus 2 greater than m sub epsilon, then this is also true. It's the same form. We just replaced n minus 1 with n minus 2, and we replaced n with n minus 1. And we multiply both sides of this, just like what we did in the previous proof. Multiply it with this expression here, and we do that because by doing it, this term here now becomes equal to this term here, and so we can make a chain of inequalities. So we start with this term, and then this term, and this term is just equal to this term, and so we can also say that this should be less than this term. So we can actually get rid of the equal sign here, but either way, this is also true, that it's less than or equal to a sub n, the absolute value of a sub n. And we can now eliminate this middle term here, and we obtain this expression, this statement. And we do that for the next term again, a sub n minus 3, and repeat the process, multiply both sides by, this time, the square of this expression, the square so that it will match this one with the square, and this is what we obtain. And we see the pattern, it repeats, and we can do that up until the subscript is k. And when the subscript is k, this is what we obtain. Now we know a sub k here is a constant for a given epsilon, and also epsilon is a constant. And here we know that L is greater than 1. Now let's think about epsilon. If epsilon is chosen such that this expression here is less than 1, what we get is that the limit here is just 0. So 0, so we just know that a sub n is greater than 0. But it doesn't tell us anything else. It's true, but it doesn't tell us anything else. It doesn't tell us that it diverges. So instead of choosing that kind of epsilon, because we can choose anything for epsilon, we are free to choose anything for epsilon. Instead of choosing that epsilon that makes this expression less than 1, let's choose an epsilon that makes this expression still greater than 1. And we can always choose that. epsilon. Again, we choose an epsilon such that this expression here is always greater than 1. And we know that L is also greater than 1. And so, by doing that, we know that this expression here now is greater than 1. And that's very good because we know that the limit of this expression here now, if this term here is greater than 1, actually is infinity. If you have something that's greater than 1 and you exponentiate that, you multiply it by itself many, many times, then you see that the limit actually approaches infinity. And now we are at the form that we desired. Infinity is less than the limit of a sub n. And that means that this limit is also infinity, because only infinity can be greater than infinity. And this limit being infinity means that this sequence diverges. And that concludes our proof for both of these tests. In this video, we've shown a proof for the ratio test for sequences. This test says that if the limit of the ratio of two successive terms in a sequence as n approaches infinity is not equal to 1, then the sequence either diverges or converges to 0. And again, this is from the contrapositive of the more direct statement that the limit, if the sequence converges to a non-zero number, then the limit is 1. So that's the contrapositive that we started with. And this test can be broken down into two cases. The first case is when the limit is less than 1, and in which case the sequence converges to 0. And when the limit of the ratio is greater than 1, then the sequence diverges to infinity. And then in the next video, we will extend this test for series. So if you recall, series are just special sequences where each term is a sum of the terms of another sequence.
Please hit subscribe.